Hello and welcome back to a new video here on the LudigFusel channel in my C++ tutorial series. In the last video we have started our journey with Visual Studio that I have not opened up yet, which is kind of like stupid, but yeah. So C++ tutorial, there we go. So we started with Visual Studio and we basically added our code that we have written all the videos that we had. We have basically put all the code inside of Visual Studio, created the project. I told you how to set up the project and everything, and here we are. We have our first code done, and we can press F5 or the button here, local Windows debugger, to start it and get our hello world. Alright, so this is basically the starting point, and today we're going to expand on that by adding variables in there and talking about data types. But I don't want to start directly and throw all the code at you and tell you, hey, this is how it works. No, we want to get to this logically and we want to see why we do it that way. So let's first start and analyze the application that we have done. And with application, I am now just mean these two lines. So basically everything that we had in here that did something that we really cared about. All the other stuff that we have around here is just to make the compiler work and to make our code work so that our code works and the compiler can read it. And basically the only thing we really care about is the hello world. So let's analyze this. What are we doing here? Well, we are printing. We are printing to the console, printf. So we are writing, outputting some data. And this is basically one step that an application is doing. Every application that you're going to have in your life is going to follow a certain pattern. And one part of this pattern we already discovered this, which is the output here, printf. So let's maybe open up a notepad, which very interesting you can also find with editor, but yeah. So here we have our notepad. So what have we done? So we have done some output basically here. So our last step, or our first step and our only step that we did in our application was outputting something. So what would you imagine doing as well if you have an output? Well, if you output something to the user, it's very logical that you also want to have an input from the user. So we also care about the input, which is something that we don't have. So basically this is to do. We don't have it yet. And basically, if you would imagine outputting, you output some data, and inputting, you input some data. So input, output. So what would be the logical choice in between of them? Because, well, if you would input something and output something, it's really bad. Because like if you're inputting something statically, you basically input some data and not dependent on the data that you have inputted, you basically produce an output. So if I would have a function called input somewhere here, and I would need to basically input something to the application, to the computer. So for example, this console window, you can basically see here now it's press any key to close the window, but you can also receive input like what you can do here in normal, in the normal CMD window. You really don't need to care what's going on here. But yeah, if I would add some input here, well, nice, I can now input some text, for example. But well, this text is it's really not cared about. This text is just skipped. We have inputted that, it might be somewhere in our application, but we are not depending on the text. So we are basically just straight going and printing hello world. So the text is kind of like useless. We need something in between to basically transform our input. And this is called the processing. So processing, which is also to do. We haven't done this. And this input, processing, and output goes to the IPO model. Input, processing, and output. And this is something really important that you should always follow. You should always follow the IPO model to make it easy to understand. So first input everything, then process the data, then output it to the user. And that's also how it's logically working. For example, if you want to open up a file and encrypt the file, you need to basically ask the user for the file that he wants to encrypt. You need to ask the user for the password. Then you need to open the file, encrypt the data, write it to a... So you need to open the file, encrypt the data, and then, if you are done with that processing, this encrypting, you need to output the file back to the user. So write it back to disk. So very logically, the most of the problems that we're going to have are gonna follow this IPO standard. And if you don't really know that, or the problem is might be a bit more complex and you have multiple inputs and stuff, then you might take the IPO model as a starting point and try to follow it as close as possible so that you get a nice and structured application. So that's really important. IPO, input, processing and output. Well, currently we're just gonna delete the input again because we don't need it for now to basically see this. We can always have a so-called static input, so an input that is never gonna change, a constant static input. It's always there, it does not depend on the user, it's not dynamic, cannot be changed. The static input, we can always simulate this. So in our case, we're gonna simulate the input for beginners. Because inputting basically requires to understand a bit of more how the other function, the opposite function of printf works, and I don't want to get to that directly from the beginning, so we're basically gonna put input back and simulate this. Alright, so let's talk about the big block that we have here, the processing block, which is by far the most important one to do, because like input, output, this is always so it's basically some stuff that we don't care. If we, for example, have a game, input and output is completely handled by the game engine. Processing is also handled by the game engine, but you basically need to extend the processing of a game engine to basically add your own game logic to the game. But input, output is always handled. Like Unreal Engine input is just a form on the editor guy, user interface GUI, and what you basically do is you tell the engine how the input should be mapped, and everything else is done by the engine. The input is pulled by the engine, the input is processed by the engine, and then basically your processing block, your game code, just gets the raw, or not the raw, but the processed data of the inputs, and you can use this in your processing to basically produce some data. And also the output, all the rendering, all the sound output, it's all handled by the engine. So processing is most of the time the thing that we care about. Input, output, we're gonna abstract this way more. So basically you're gonna try to put this far away from your daily code base. Now we are basically starting with inputting and outputting, but later on in the future we're basically gonna put this input and output way away from us. We're gonna see how this works in the future videos, but basically we try to move this as far away as possible and to abstract this. So if we have multiple platforms or multiple types of input and multiple types of output, we want to find a common feature set so that we really don't care from where the input is coming or where the output is going. So that's basically the point of that. Processing is the most important thing that we need to care about. So what does processing involve? Processing, let's start this out here. Processing does revolve multiple things that we need to be able to do. First, we need to basically transform the data. Transform the data, for example, with equations, or most of the time equations. So mathematical equations that help us figure something out. Does it really need to be mathematical, or does it really looks very mathematical? So always like fx equals 2 power over 2 plus 5. Does it always looks like that? No. Processing can be, or transforming the data, does not really need to get down to the math, but what we basically do is we have data and we modify the data. And modifying this data can either be by basically having a function f from x, so a normal function like you would have in the math. Could be as simple as that, but it could also be as complicated as calling Microsoft APIs. For example, if you have DirectX 12, ID 3D12, device, and you basically say render or draw, for example. Processing can also be done by basically invoking all these commands. Even that draw is kind of like already like outputting something, but it really is not if you are in the context of DirectX 12, because that drawing in DirectX 12 is not outputting. But you get the point. Like, you could have a math equation, you could have another software component that does do something for you, so something like printf, but then it doesn't print. It basically does something else for you and transforms data. Like, for example, if you want to have a sine function from x or a cosine function from x, this is like something that you don't implement on your own. Sine and cosine is implemented somewhere else. Same with like power x over 2 over x, for example. Like, this is all like some functionality that has been abstracted away from us as the programmer, but you basically use them. So transforming the data is somehow possible, required. And if we transform the data, we basically need to store the data. So store input, output, and intermediate. So we basically need to store the data. If we are doing an equation like f from x equals 5 over x over 5 plus 5x plus 5, for example, if we would have an equation like that, then we basically need to have a way to basically store x, then we need to store f from x, and then we might need to basically output this. So an application would be something like, we would basically have some input x, store the x, store the result of f on x, and output f from x. Or like something like that. Store y equals f from x, and then output y, import, let's say I, and then store x equals I. So something like that. We basically need to be able to store our intermediate values. We need to store our input. Our input as I needs to be stored somewhere. We need to store the result of our computation. We need to output it. So we basically, aside of transforming the data, we need a method of storing data. And today we're going to learn one way of storing this data, which are going to be variables. Variable. A variable is something that can be variated over the runtime of the code. So the variable is basically just a label. So it's a label to a value. And this value can be runtime changed. So if I do something like hello in these brackets here, this is a static value. It is static and constant. It doesn't belong to anything other than our application, and it's constant. We can't change it. We cannot really say, oh, I don't want to have this hello now at runtime. We can just say something like hello you world, something like that. We can do this, but this is like all done at compile time. The user cannot change it. We cannot influence this during runtime of our application. And that's the point. Variables are, most of the time at least, meant to be changed at runtime or to be calculated at runtime. So if we would basically go the route that I've just done, so if we want to have our input I equals something, then we would basically need a way to basically tell the compiler that this I is going to be a variable and is going to be stored. And how are we going to do this? Well, to basically declare this variable I, or to basically define this, because by default I is just a random text. I is no identifier. If I would basically define I like we did it up here at a point, then I is kind of like usable, even though we use it in the wrong way here. But you can like see from the color highlighting that I is now recognized. If I hover over this, we basically see this. We can basically search this. If I remove this again, hover this, it just says identifier I is undefined. And that's, by the way, the nice thing of an IDE. It tells you the errors before you compile the application. So as you can see, we have the I here. It says undefined identifier because the compiler is not aware what I is. So if we use these functions like printf, we previously had all the signatures. So basically we told it the signature is going to be int main, and it's going to be a function. Why ever we had this int. And how are we going to do this variables? Well, a function always had these opening and closing brackets. So if I would declare like a function, we would do this like that. But now let me actually declare this as a type. So function would be something like that, to declare it as a function. But if we don't want to declare this as function, we're going to remove the opening, closing, and brackets. So these things, we're going to remove them, and if we remove them, we basically say, hey, this is a variable, this is not a function. And now we are one thing missing. We are missing the so-called type. So each variable needs to be a type. And as you can see already, if I type this like that, you can basically see that now the I is identified. And if I hover over it, it says local variable, because now I have declared it as a variable because I basically gave it a type. So type I, which says this is the type and this is the name of the variable. But if you hover over that, you can basically see error type, because type is not recognized as a type. And if I hover over that, identifier type is undefined. So a type is an identifier as well. So now, how do we get this type? Well, there are, of course, ways to define your own types, but there are also built-in types in C. There are many of them. I'm gonna show you a few of them, the kind of like classical way to do it. So if I would now write something in that we already had up here, as you can see we have this int, where I always told you don't really think about what this is. And actually this int is a type. If I hover over that, I get nothing. Yeah, but this is actually a type. And if I would now replace this type by an int, you can basically see that now the error is away. And if I hover over that, it says local variable int I. And now what I can do is I can assign I a value. So I equals something. So now what do I want to assign I? Well, later on we're going to use a proper inputting function. Now I told you we're going to start by simulating the input, and I could just say, okay, I'm going to set the input to be 5. So as you can see, 5 worked here because we basically specified an int. An int means integer, and integer means a normal number, so a number which is negative or positive. We're going to get to how far this can go in a second. Int is not the only thing that we can use. There are also different types. For example, we could say short. Short means basically a short integer, so a smaller integer, something that is not as big as an integer. We're going to get to what big and small means. We could also say char, which is a character, which is even smaller than a short, or in theory should be even smaller than a short. There is a long. If we need something that's longer than an int, okay, we can have a long. If we need something that's not even longer, we can say long, and we have like double times the long and an even longer type. And now you can basically see that this is really confusing. Why is that confusing? Because like we have all these types. So for example, if I would show this to you, what we have char, c, int I, or even forgot even the other thing, short s, int I, long l, long ll, and yeah, it's a madness. So that's really, really bad. But before I'm going to tell you what really is bad on that, we need to basically... So these names are really not really these names are not really telling anything. The only thing that they tell is basically a char is small, a short is a bit bigger, a int is bigger, a long is bigger, and the long is even bigger. So, well, it's really not telling us anything that we want to know. So actually, this is not how we do it. This is not the way to do it properly in modern C and even C++. You can always do this. You can always have these char, short, I, int, long. You can always have them. It's not an issue. You can have them. But anyway, let's put this to input here. So you can always have them at a value that you want. So you can always have them, it's not an issue, your code will work. The idea of doing it like that has some advantages, or had some advantages previously, but people are gonna go away from that because the disadvantages of these things are more compelling than the advantages. So to understand this, we need to get a bit further. How are computers representing numbers? Okay, we haven't learned comments yet. So how are computers representing numbers? Let's go back here to my notepad and try something out. So if I have the number 5, how is the computer gonna represent that? Well, how are we representing it? We, as humans, are representing this by counting up. So we would start counting 1, 2, 3, 4, 5. And now we are at 5 and we know what 5 is. But how do computers work? How do computers count? How can I represent 5 and count up to 5 by a computer? Well, we humans have a so-called decimal system. Decimal stands for like base 10 system. Base 10 means that we have 10 the chars for representing numbers. We have 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. These are all the things that we use to represent our numbers. If we are counting up like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and we kind of like are on the maximum number that we can use to represent numbers in our systems. Well, why? Because we have 10 fingers, so we count from 0 to 9. And now as soon as we have reached the 9, we are out of charts. And what we do is we basically start another digit. So the next one is 10 or 10, because 9 was the maximum that we could get. So we need one more digit, 10 equals 10. And then we start over and we do it all along until we get to 19, where we are also out of charts again. So we basically need to go to the next digit and we need to increment this as well. So we start by 20, 21, and the journey goes on until we at some point are like at 99 and the next thing would be like 100. So as you can see, we basically go on until we kind of like reach out of the char, so in our case 9, and then we go to the next digit. So how are computers working? Computers work a bit different because they are binary, which means base 2. Because computers are electrical devices, and in an electrical device, a binary state means on or off, so voltage supplied or not supplied, on, off, 0, 1. And because of that, the computers only have 2 states to represent something. Well, if we start with 0, it's very simple. 0 is representable on the computer by meaning off. So if I would now want to go further and also represent the on state, we will basically now say, okay, 1. 0, 1, okay, voltage off, voltage on, 0, 1. Okay, we can count like that. But what is now if I want to represent 2? We cannot represent 2 because there is no, it's not another voltage state. We need to add another digit. And well, how does it work? Well, we basically add another digit, which means 1, 0. So our 10. But we don't really say 10 as programmers because 10 is kind of like decimal. So basically we say 1, 0 on binary. So 1, 0 would mean 2. How would that go on? Well, now we would use again the other digit and would be at 1, 1, which means 3. Now, if we would count up again, okay, 2 digits already used, so 100 or 100, which is what we were at 1, 2, 3, 4 is 4. So next thing would be 101 or 101, 110, 111, 1000, 1001, 1010, 1011, 1100, 1101, 1110, 1111, 1000, and so on. So we do the same thing here that we have done on our decimal system, like how humans count, but we basically do this with like less possible chars. So we only have 0 and 1, so we basically need to count very more early. So this is basically how computers count. And if we would now want to count up to 5, we would basically have something like, let's start with that, 0, 0, 0, 0. We always tend to fill the empty zeros as well. And we would start counting because we would start by at 0 here, the computer. So I didn't have this up here earlier on, but we would have this here as well, 0, 1, 2, 3, 4, 5. And what I would basically now do here is on counting, I would say 0, 0, 0, 0. Now, okay, I'm at 0. Let's maybe pad this so that you can see what's going on here. I don't think that we need these anymore. You should have understand this at this point in time. So let's maybe add a bit of formatting here. So there we go. So let's count up to 1. Okay. Let's count up to 2, 0, 0, 1, 0. Let's count to 3, which is 0, 0, 1, 1. Let's now count to 4, which is 0, 1, 0, 0. And let's do another increment here. So 1, 0, 1, 0, 1, which is then our 5. We have now reached our value 5. And yeah, that's basically how the computers store these numbers. Why am I going to tell you that? Well, because of one thing. To basically be able to store these numbers, you need some storage. So the computer basically needs a way to store these 0 and 1s. And a computer stores these 0 and 1s in bytes. Bytes is the unit where computers store data. And each byte contains 8 bits. And a bit is basically 0 or 1. So computers store data in bytes, and each byte basically consists out of 8 bits, and a bit is 0 or 1. So a bit is basically the minimal unit, so voltage on or off, and 1 byte basically stores 8 bits, or if you would want to represent this somehow, 0, 0, 0, 0, 0, 0, 0, 0. This is basically how a byte would be stored, for example. A simple byte, the most easy unit that you would have in a computer. And basically, this is how computers work. So if you would have these 8 bits, what could you represent with them? Well, you could start at 0, for example, and you could go up to, all of these are 1. If these are all 1, we can do a simple math. Let's open up the calculator here on Windows, and let's do a simple math, which is basically 0 to 2 power 8, so 8 over 2. So if we would do this here, I think the calculator does not do this in the simple mode. Let's go to scientific and it should be able to do it. Yeah. So let's do 2 power 8, so 8 over 2, and we would be at 265. And since we also have the 0 in here, we need to make sure that we subtract -1 here. So basically this would result us in a 255. So with 8 bits we could represent numbers from 0 to 255. Yeah, that's nice. We can represent some stuff with that. But what happens if we would need a negative number? How would we do negative numbers? Well, we could use a different representation. We could, early on, we basically used them here as decimal, 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 decimal. So these were kind of like used to binary represent our decimal state. But we could also, let's maybe put these down here as well, so that this is nicely formatted. Okay. But what we could do is we could represent them differently. We could represent them with a sign and decimal, 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 decimal. And by adding a sign, we basically say this digit here, this single bit, represents if the number is negative or positive. And we basically always say if it is 0, it means that the number is kind of like positive. So all of our positive numbers would now basically evolve to 0, 2 power 8, this is what we had previously, but since we now have a sign bit, so this one is already used for the sign, we need to basically subtract -1 here, so something like that. 8 minus 1 over 2, and of course we also need to represent the 0, we need to subtract 1 again, which would mean if we would do the math, let's do the math here, so we would have again 2, 8 minus 1 is 7, so 7 over 2 means 128, so we subtract the -1, means 127, so 127. Now we also need to take a look at the negative range, so we don't need -0, so -0 does not really make sense. So as soon as this bit is kind of like one design bit, we kind of like represent -1, for example. It's actually a bit different. Later on you're going to see this, but in theory you could represent this as soon as the sign bit is like negative or 1. As soon as the sign bit is 1, it indicates that it is negative, the number. We could say we are at -1, and then we basically count down to some value that is smaller than 0. So how would we do this? Well, now we basically have again 2 over 8 minus 1 bits available for our negative values. But since we don't need the 0, we don't really need to subtract anything here. We still have the value here in the calculator, so we have 128. We don't subtract anything, so our most negative value is minus 128. So by basically selecting how we're going to interpret these bits in a byte, we can basically see how the number looks like, what the number is. And yeah, that's quite nice and that's really useful. But as you can see, it is not really possible to do very complex calculations. We have a maximum of 255 and we have a maximum of minus 128 and 127, depending on what we use. So we really don't get far with that. We just have very simple integers. We can't just really represent the simple stuff. And this is also what people saw on the first computers. First computers that use 8 bits. And later on what they added are extensions to also support larger numbers. How can you support larger numbers? Well, we can actually combine bytes. So if we would take a byte and another byte, we could get something like 2 bytes. And if we have 2 bytes, our values are going to be way more extreme. Because if I would now do 2 power, what do we have now? Now 2 bytes, so 8-bit plus 8-bit means 16-bit. And this means that we have now 16 over 2. And now the value is that large value that we have here, minus 1 to represent the 0. Can copy this over. And now we have 65,000 that we could use. And of course we could also now do this with negative numbers as well, with a sign bit, but yeah, we could like add 2 bytes together and this would be nice. Now this would be kind of like a 16-bit number, and well, we could carry this on for quite a while. So for example, we could take now 4 bytes. You really don't take 3 bytes. Like, you would now think that I might now say, okay, 3 bytes. but 3 bytes is not really something that you want to use, because 3 byte is not really matching the computer, and the computer always uses power of 2. So the computer kind of like uses 1, 2, 4, 8, 16, 32, 64, 128, 265, 512, 1024, and. So the computer is always working with these power over 2 numbers. So the next thing that we would have is like 4 bytes, which would be something like, we could call this like 2 times 16-bit, so you always like double the number. So 2 times 60-bit, and this would basically mean that you would now have a 32-bit number. And by having a 32-bit number, we could do the math again to 32 over 2. And you can see this is now really escalating quite heavily. So this is like 4,000, 4 million, no, 4 bit, what is it? 100,000 million, billion, yeah, okay, billion. So 4 billion, whatever. So 32-bit, quite far. And you could even bring this much further. So let's say maybe we want to have 8 bytes. If we want to have 8 bytes, we would have like 32-bit plus 32-bit equals 64-bit. And if we would do the math again, so 64 over 2, we would get this now highly escalated number, which is like, what is that? 100,000 million, billion, trillion, whatever. I don't really know, but it's a fucking large number. You know, as you can see, as soon as we kind of like take up these bytes and combine them together, we get higher numbers, so more range for our numbers. Of course, if I want to have the negative numbers, you can see that I need to basically, basically would need to do the math again for getting the minus values. But you kind of like get the point. So we really have options here. We really have them. And as you can see, every time we kind of like double our bytes, the numbers are not doubling that we can get, they are like growing. Is it exponential? Yeah, probably exponential. I'm not really a math guy, but I know my math that I need. So the growth is really big. It's kind of like doubling. Is it doubling the digits? Yeah, it's as you can see, it's like doubling the decimal digits, kind of like doubling them. Not like really doubling them, but you could compare this. So by basically just doubling the storage that you need for these 2 bytes, 4 bytes, doubling the storage, 4 bytes to 8 bytes, doubling the storage, we get way more numbers that we can deal with. Way higher numbers that we can deal with. And the nice thing is, well, if you have a 32-bit computer, your computer is natively dealing with 32-bit numbers. If you have a 64-bit computer, which every one of you is probably going to have, your computer is natively dealing with 64-bit numbers. So this is like native to your CPU. Your CPU can do 64-bit numbers as fast as they can do 32-bit numbers, as fast as they can do 16-bit numbers, and as fast as they can do 8-bit numbers. And, well, that's a nice thing. You basically get this for free. On a 64-bit system, you get 64-bit for free. Of course, if you store always 64-bit numbers, you always use 8 bytes. So if you could use something which just needs to be 0 to 10, for example, you could just use an 8-bit number and just use 1 byte. And then you could like store 8 of these 1-byte numbers instead of one big 64-bit number. So you basically have always the idea switch between. So what you always need to do is you always need to basically match your problem to the kind of like width of the numbers that you use. So if you have an issue that is quite small, that doesn't need very much bits or high numbers, you can use an 8-bit number. If you use something that's like counting every millisecond or counting every second up, and your application might run very long, you might just use a 64-bit number, and you kind of like should get the point by now. You have kind of like this trade between using the storage for the numbers or between having a limited range of numbers available. And yeah, that's basically how numbers in computers work. We also have the option to store floating point numbers, so to do floating point computations with them. So 3.5 divided by 1.2, for example. But these combinations are a bit more advanced, and we're not going to go into the detail how they are represented by the computer. You can do this, but this is always a thing that you really don't need to understand. There is a format that the computer is using to store floating point numbers, and there's optimized hardware that can do math on floating point numbers, but how this works is really not that important for us. Alright, so how does these things like these, let's summarize this maybe as 8-bit, 16-bit, 32-bit, and 64-bit. How does these values map to what we got here? How does that work? Well, a char is most of the time, let's maybe write this in here. A char is most of the time 8-bit. A short is sometimes 16-bit, or many times 16-bit. Int is most of the time 32-bit, and a long is 64-bit, and actually a long as well. But these things that I've just written down, like what this char, short, int, long, and long is, it is really not guaranteed. The thing is that it depends on the compiler. These values here, this char, short, int, long, this is dependent on the compiler. The compiler can decide how many bits it wants to assign to that number, or how many bytes, how you want to see it. The compiler can decide what it's going to do. And the nice thing is that's not even consistent. So if we are up here, we had the selection between x64 and x68, which basically means 64-bit or 32-bit. If we change this here, the width of these types are going to change. So it's not guaranteed. If we basically say, all right, I now want to basically store like 16 bits. I want to store 16 bits just to have these 16 bits, and I'm going to use them in a way. So I just want to have plain 16 bits. I just want to use them to store like 16 states, and the states can be on or off. So basically I abuse the short to not store a number, but basically store a different representation. We can always do this. That's a nice thing. C++ allows us that we can do this. C as well, of course, because like it's nearly like similar. But they allow us to do manipulation on bits. We're not going to get to this in the near future. Maybe in the near future. We're going to see. We're going to get how to manipulate bits in the future, but you can do it at least. And now it would be great. And you would say, all right, I'm going to use this short, and I'm going to use this for a flag. So I'm going to use this flag 16s because I'm going to have 16 values that I want to store in here. It works on your computer and everything is good. And then somebody tells you, hey, can I get a 32-bit build of your application? And you say, all right, good. Yeah, you're going to get a 32-bit build. I'm going to change this here, and I'm going to ship you the application. And your user would try to use the application, and it crashes. Or it doesn't work as intended. Why is that? Well, because as soon as we change the configuration, these things might change. And this is an issue that many applications suffered from. They used 32-bit before we had 64-bit. They used 32 bits, and they used like the asserts that the characters are from these types are from a different width. So they basically said, okay, the int on 32-bit systems is like, let's say, 16 bits width. So they basically used int as a flag here. And then they changed to 64 bits, and their whole memory layout didn't make any sense. The data was not there where they expected it because all the width changed. And this was like one main reason why many applications took so long to basically be ported from 32-bit to 64-bit, because it was not just flipping the switch here. It was more about maintaining your whole applications and removing all of these nifty bit accesses to make sure that you don't like exceed the range or screw up your whole application because the types are no longer as long as you expect them. And yeah, if that happens, it's bad. So what we basically have done, we have learned from that era, and we basically say, we are never gonna use these types. We're never gonna use them. There are special types that are always guaranteed to be of a certain width. And these types are defined in a header. So something similar than this stdio, we talked about that. In that header, basically we had the printf defined, and there's another header that has these nice types defined. It's called stdint.h. stdint.h. If you really don't know how to type this, you can press Ctrl space, which brings up the suggestion bar, and you can type std, and then you can basically scroll a bit around here, and you would find stdint as well. So yeah, stdint defines our types, and the nice thing is that stdint is very simple to use. So what do we want to use? Well, we want to have an integer, a normal number. So I can type in int, and the nice thing is now I basically want to specify how wide my integer should be, and I just want to say, okay, I want to have a 32-bit integer, so I'm going to write int 32, and then I can add an underscore t, which stands for this is a type, just a convention that people like to do it, to have underscore t behind the type. So I want to use a 32-bit integer here, and I want to call it input, and now it's guaranteed that this integer is always going to be 32-bit. And if I hover over that, you can basically see that this is defined as typedef int int32t. Basically what stdio does, it is basically a header supplied by the compiler, and the compiler always knows which of the standard types that we had, like this int, char, long, the compiler basically knows how wide they are, and depending on how wide they are basically populating this stdio header, and we have a portable way between different compilers, different compiler versions, different platforms, different computers, vendors. We have basically a static way to define static with integers. And of course they work for everything. So I can have an int 8t, I can have an int 16t, which it doesn't like now, but I can have it of course, like int 16t. I can have the int 32-bit 32t, we already had the 64. And do we also have a 128? No, because 128 is not supported by any computer. We only have 64-bit processors, so 128-bit is not defined there. Alright, so basically what we now have used is the default int. The default int always works like that, so it always goes from negative a number until to 0 until to a positive number, which is one smaller than the negative number but with a positive sign. So by default we are always using the so-called signed integers. They are signed because they have this sign bit. If we don't want to use them, we can specify them as unsigned. So you could try to, if you would have like a normal int, you could say unsigned int here. So basically all these standard types, they are possible to basically add this unsigned word before them, unsigned long, unsigned short, unsigned char, unsigned int. This all works. But we of course want to use again these nice types, and these types you cannot just say unsigned, because unsigned is only defined for built-in types. But of course the standard library has them defined as well, and they are basically just defined as uint, because u stands for unsigned, and we also don't want to type this out every time, programmers are lazy. So we have ints and uints. And by basically having them, we could basically now store this input. So we now can simulate this input, which is the input, which is equal to 5. You also have the option to write this shorter. So now what I basically have done in the line 1, I have basically defined this variable input, and I have given it the type uint32t. Now after that, in the next line, I've basically written input equals 5 to basically assign this to the value of 5. And 5 is again a static value. But you can also make this in one line. You can write this basically uint32t called input equals to 5, which makes this a bit easier to read. There are different conventions. There are people that like to define all the variables at the top of the function and then assign them later on. It's just how you like it. And now our applications are getting a bit more complicated, so what I want to show you is how to write comments. You are able to write comments. A comment is basically a section in your source code that has been ignored by the compiler, so something where you can write everything you like. There are two types of comment. There are single line comments, which are just applying to the current line until the end of the line, and there are multi-line comments that basically start at a certain identifier and stop at a certain identifier. We're just going to use the normal single line comments for now, and they are indicated by writing 2 slashes. So if you write 2 slashes, you can see it's kind of like getting green, everything that you write, and you could everything you like. It's automatically a comment that is ignored by the compiler. So you could add a label like simulate input for now, simulate input to do replace with proper input. Could do something like that. Alright, so something like that, input equals 5. And now what we want to do is, based on that input, I want to do a calculation. Maybe let me make this a normal integer again to just be safe. Alright, so now we have our input, and this input is equal to 5, and this input shall correspond our x that we then input into our function. So now, maybe let's add the I so that we have the IPO later on, like here. So P and O, so IPO. That we had. Now we basically simulated the input, and now we want to process something. So insert to y equals, like we had this, f from x, like that. Does that work? No, because we don't have f. This is already here. Yeah, this is basically what I wanted to do. Actually, this is not what I want to do because this requires some advanced stuff that we don't want to do. Let's do x times x, something like that. This is a bit more simple. X times x plus 5x equals that. So this is our f from x. So could you do something like that? No, this doesn't work. If we want to have f as a function, like in a proper function, like a C++ function, we will need to do this differently. We're going to not do this like that in this video. We're going to have functions as well in the future. So what I want to do is basically do this like that. So I want to define that y equals x times x plus 5x plus 5, and you can see we still have an issue here. It seems like that this seems legit because it doesn't show us an issue. Also this plus 5 seems legit, this plus also seems legit, but 5x, it's not recognized. Why is it not recognized? Well, because you can't really type 5x. 5x would now need to be an identifier, which doesn't really work because identifiers can start with numbers, so you can't have a variable called 5x. This doesn't work. An identifier is always only allowed to start with a character, but after that you can of course have a number. So you can have x5, but do I really have x5? Because x5 is really not, it's not really meaning anything. It's not, yeah, as you can see, it's also, if I add this like that, it's like not really saying that it's working. So x5 is really not something that is a point. So 5x, x5, we really don't care. So what we just need to do is we need to explicitly add the multiplication there. So now we basically have the equation here, y equals x times x plus 5 times x plus 5. And this is basically now computed and stored in y. Then we have our output here, and we print hello world. This really doesn't make any sense anymore. We don't want to print hello world. Okay, yes, we might want to do this, but we're going to delete at least one printf, the other one we're going to abuse and reuse. We want to print now our y, like that. And it seems to work. But what happens if we start the application? Let's see. Boom. Bad things happened. The compiler worked because we are currently executing application. If you are getting this exception thrown, this means that the application is executing. You can also see that we have like this stop sign, discontinue, and the process, thread, like simple capp.exe. You can kind of like see that we are running our application. Our application is currently executing, but it gets an error. The error is basically here. It's inside of this function. You can't really see this. If I would click on this here, this is basically what is currently going on here. This is called a call stack. You can like click through that if you want. And the call stack is currently what's happening, and we are currently in some Microsoft code. This ucrt-base.dll is a DLL supplied by Windows, aka Microsoft, and basically not our code. So something went wrong in Microsoft's code. But you can always trace this up here, and you at some point get to something that seems a bit more legit, like the simple C app. Simple C app means, okay, this is now in your application, and you can click it and you see what's going on. And you can see that this is something going on in the stdio.h. So even though this is like a Microsoft thing, it's kind of like in your application. And as you can see, you can see what would happen next. So this error means this is what happening next. And because this is at the end of this bracket, means it's the end of the subroutine or the function called vfprintf_l. Why are we calling this function? We're going to get to this in a few seconds. This is basically our printf. And this printf is basically calling another printf function called stdio, vfprintf, which is basically the Microsoft implementation of printf. And this Microsoft implementation of printf had an issue, and the issue was an exception, and the exception was thrown at ucrt-base.dll, so inside of this Microsoft code, while working on the simple capp.exe. And the error was 0xC0005 access violation reading location. This 0x is a special format of numbers. It's something in between a decimal and binary. It's called hexadecimal. You really don't need to understand how this is going on. It's just something similar to binary or decimal. We might going to get to this in a separate video. And to basically figure out what's going wrong, you basically need to work yourself up this call stack until you get to something that you understand. So let's go one thing up again. Okay, what is that? VF printf. Oh yeah, okay, now we are in the function printf, and the function printf is doing some stuff and calling this underscore VF printf underscore L. Okay, so we really don't understand what's going on here as well, so we're gonna go one up again, and now we are at something that we can understand, and you can see the next thing that would be done is like this closing bracket, which means that we are currently inside of printf, and printf had an error. And yeah, why do we have this error in printf? Well, we are using printf not the right way. By the way, you saw me clicking on that red stop button. This basically means stop debugging and returns to normal code operation, normal coding. So what is wrong with that call of printf? Well, printf doesn't work like that. You can't just put anything that you like in printf. Printf always works with a so-called format. This string here that we had up here where we had our hello world, this is a format. And by having normal text in here, it's totally fine. You can have a format that just outputs normal text. But what we can also do is we can add a special char, which is like, for example, this. In case of printf, the special char is the percentage sign. So percentage means, hey, stop printing this normally. And percentage means now we want to print something special. And the special thing that we want to print is an integer. So we're going to type in I, which means, hey, here we want to print an integer. And how are we going to supply the integer? Well, we can add more arguments to that. So we can add a comma and then the name of the variable. So y. So this basically tells, this call of printf basically tells the C library, okay, this is the special char I, which basically tells that, okay, print an integer. And what then this would do, it would take a look at what's here, so the next variable here, the first one in this case, because it's the first special char that we have reached, and in this case it finds the value of y and then it prints the value of y. And now what we could do here to make this a bit more interesting, we could say f from x equals y. Now x is also a dynamic value that we are going to later on input. Currently we are simulating this, but later on we're going to input this. So we want to also put a percentage I in here to basically have this as a magic value. Now you can already see that you get these green underlines, and as you can see, Microsoft is currently detecting that we used 2 times the special character, but we are only supplying one variable down here, which doesn't work. So we also need to supply x in here to make this work. But this is now a big mistake, because now we are supplying y and x, and if we would now like copy this over to here, we would get f from y equals x, which is not what we want. So we basically need to flip this to x and y to get f on x equals y. So that will now replace back in the percentage signs. And if you are doing this like that, you then now have your full IPO. Not really full one, but yeah, inputting, simulating a x equals to 5, doing some computation, and printing a nice f from x equals y to the screen. And if I would now execute this, you can see that we have the f from 5 equals 55. If we would do the math, we could do like the math here to verify that everything works. So let's open up the calculator. So what do we had as an equation? We had 5 times 5, 5 times 5 equals 25. And then we again have 5 times 5, so another 25, sum them together 50, add another 5 on top of that is 55, and f from 5 equals 55. So yeah, the computer can actually compute stuff. That's why it's called computer. It can compute, calculate values. Yeah, and that's everything that we need for today. We basically discovered how to use variables, at least like normal integer ones. We're gonna have a separate video when we go into like strings and other fancy stuff that we might want to use. But now we basically were able to use basic numbers in the computer, and that was nice. So yeah, thank you for watching. We're gonna see us in the next video. Have a nice day. Make sure to like and subscribe, and see you in the next one. Bye.